So let's review that. This is the wave-particle duality expression as given by de Broglie, p equals h over lambda. But k, the wave vector is 2 pi over lambda, so you do some substitution, you find k is equal to p over h bar. Here we introduce a new symbol, which is very often used. H bar is defined as h over 2 pi. Okay, that's our new definition. Often we see this combination h over 2 pi, so we might as well just give it a new symbol called h bar. K equals p over h bar. So so we have old math and new physics. Old math is the Fourier analysis. The new physics is that this k vector, this wave vector, has actually something to do with the momentum of the particle. In fact, it's proportional to the momentum of the particle. P equals h bar k. Now, we know that delta x times delta k is of the order of 1. What does that tell us about delta x and delta p? P is h bar times k, so it's of the order of h bar. And let me box that. What does that mean? It means that since we're using the wave to describe a particle with the wave vector k being proportional to the momentum of the particle, if we find the particle to be very localized in real space, which means it's very concentrated, you cannot find it anywhere else, so delta x is very small, then strangely enough, the momentum of this particle has greater amount of uncertainty, okay, because it's more spread out over a greater range of possible values. That's delta p. Delta x times delta p is of the order of h bar. In particular, if delta x is known to be 0, which means the particle is extremely concentrated, it's just at location, say, x equal to 0. It cannot be found anywhere else, so delta x equal to 0. According to this expression, this side, no matter how small it is not 0, right? That means delta p goes to what? Goes to infinity, okay? Therefore, we say this particle can have all kinds of possible momentum values. It is impossible to pinpoint what the momentum is. And therefore, it is impossible for us to know precisely where the particle is and what the momentum of the particle is. In other words, how fast it is moving. We do not have the privilege of knowing both the location and the speed of the particle with 100% precision, as we took for granted in classical physics. This is a stunning example of the so-called Heisenberg uncertainty principle. It was first discovered by Werner Heisenberg. The year was 1927. So I took the liberty, I went out of my way, used a few pages, a lot of your time, to give you examples of the Fourier transformation, especially highlighting the contrast between the behavior in the k space and x space. What I try to get, two things. Okay, first of all, the Fourier analysis was an old classical theory of mathematics. For any waves, we find delta x times delta k is of the order 1, which means in order to construct a wave out of a k space, we have to use a range of k values delta k, and the more concentrated the wave is in x space delta x, the broader the wave spectrum in k space delta k would be greater. This is old mathematical theory, okay? But here we have something new, and that is this k is not just a wave vector, rather it is proportional to the linear momentum of the particle, and therefore delta x times delta k becomes delta x times delta p. So once again, let me write that down. Delta x times delta p is of the order of h bar. In fact, it can even be greater sometimes, depending on how we construct the wave, but it cannot be 0. That's the point. It cannot be 0. More precisely, when you study the Heisenberg principle in more precision, you find h bar over 2. But roughly the order of magnitude is h or h bar. This expression, the Heisenberg uncertainty principle, puzzles a lot of people. Because in classical physics, we never had to worry about this. If we have a particle, we can use Newton's second law to exactly figure out how it moves, and therefore we have its acceleration given the force. From the acceleration, you can find the velocity, of course, its momentum. And of course, at the same time, the location of that particle is also given because we can find x as a function of t. So therefore, at least in theory, we can pinpoint where the particle is. We can also find exactly how fast it moves. So delta x and delta p can both be 0. There is no uncertainty in principle. If we do a correct calculation, a correct measurement, we know where the particle is and we know how fast it moves and in which direction it moves. But in quantum physics, that is simply not possible. This is nothing new mathematical, but it is new in physics. And that is, we use a wave to describe a particle, and the wave vector k of that wave corresponds to its linear momentum. That is wave-particle duality. And from that, and because of the old theory of Fourier transformation, we are forced to accept this uncertainty principle. So you see, the uncertainty principle actually has its root deep in the wave-particle duality. It is something we can derive from wave-particle duality. And the wave-particle duality, therefore, once again, we saw it to be at the very center of our idea of quantum mechanics. So this is nothing strange if you accept the notion of wave-particle duality. Now, how come we never had to worry about it in classical physics? That is, you do an experiment, right? You do a physics one-day experiment. You see a ball rolling down an incline. You say, oh, I know exactly where the ball is. Therefore, I must have lost track of how fast it moves. That's ridiculous, right? How come we never had to worry about it? It's because even though the product is not equal to 0 according to quantum mechanics, it is indeed very small. Okay, h bar over 2, or let's say the order of magnitude is h. H is how much? H is 10 to the negative 34 joule second. That's how small it is. Such an incredibly small number. And in the macroscopic world, we're dealing with meters and seconds and so forth. This is incredibly small. We don't have to worry about it. So that's why people never discovered it until 1927. Okay, but in the atomic world, we're looking at very small particles moving with very small amount of momentum compared with macroscopic world. So therefore, x and p themselves are very small, and even this small number of delta x times delta p may be significant for that particle in comparison to its actual momentum and its actual position. So this is something we must consider in the atomic world, the uncertainty principle. And the uncertainty principle here in this particular expression relates the momentum and the position of the particle in the x direction. It is not limited to this expression, however. The uncertainty principle always pits one variable against another variable. These are called conjugate variables. Okay, conjugate variables. In this case, delta x times delta p, I should say delta p x, the x component. Okay, delta x, if you multiply delta by delta py, there is no uncertainty principle. There is no such thing as delta x times delta py must be greater or equal to something. But there are other pairs of conjugate variables, such as delta y and delta py, satisfy the same thing. Another famous pair of conjugate variables is delta e and delta t, e and t. So we have delta e times delta t must also satisfy the same Heisenberg uncertainty principle. We did not derive it here, but this is also something extremely useful in quantum mechanics. You know what that means? It means I have a particle, I found a particle, and does not exist very long, okay? It does not exist very long. I can only capture it for a brief moment. So within this very short time interval, the particle existed, and then let's say it died, disintegrated into something else. So delta t is a very small number. And since delta E times delta T cannot be any less than h bar over 2, I found there is an uncertainty in the energy of this particle. Okay? The shorter delta T is, the greater the uncertainty in its energy. Now, it's impossible to have, say, only 1 eV of energy and 100 eV in the uncertainty of the energy, right? It doesn't make any sense. You can do the other way around. You say the particle has roughly 100 eV of energy and it's a plus or minus 1 eV uncertainty. That makes sense, but you cannot do the other way around. So if it's got a 100 eV of uncertainty, then it must have at least 100 eV of energy, right? So therefore, from this expression, we found that if a particle has a very short lifespan, then during the lifespan, the energy of that particle cannot be all that small because E is of the order of delta E. If delta T is very small, delta E must be considerably large, and that's something we will see in our example later. In our textbook, we also discussed how to use waves to describe behavior of particles. We started out with a single simple harmonic wave, so that's an infinitely long wave train with constant amplitude, and so basically you have a single value of k leading to an extremely extended simple harmonic wave in x space, as we saw that before in our lecture as well. And then it proceeded by introducing the idea of what's called wave packet. Okay, at the simplest way to construct a wave packet, here's a wave packet. Wave packet doesn't have constant amplitude in x space, rather it's more concentrated here and it dies down. So you have a wave packet whose range is roughly delta x. Okay, and if a particle is described by wave packet, then you have some idea where it is. It's more likely to be found between here and there, instead of a totally delocalized simple harmonic wave, in which case you just have no idea where the particle is. Okay, so the textbook then used some simple math to add two sine or cosine waves, and that's what it gets. You get a wave that is no longer simple harmonic, rather its amplitude itself varies as a cosine function of time, and it looks like this. Cosine function of time and space looks like this. So you have a wave which describes the profile or the envelope of the amplitude of this particle, and I can roughly, if you did that, that's what you're going to get. And from here to there, this argument, the angle phi, must change by how much? By pi, okay? Because the wave function, the blue curve itself, when it totally repeats itself, is 2 pi. So from here to there, it's about pi. And therefore, for the same moment, so t is the same. If you look at this profile, for that one moment, only x changes between here and there. So how much is delta x between here and there? Well, the angle phi changes by pi, and here's the angle phi. Delta t is 0, because I'm taking a picture at the same moment, and therefore we say delta k over 2 times delta x. Delta x is the distance between here and there, delta x, is equal to pi. Okay, so we have delta k times delta x is 2 pi in this case. So once again, I see the opposite behavior of a wave in x space and k space. Here I have two simple harmonic waves, one with k1, the other with k2. The difference between these two k values is delta x, is delta k. So delta k roughly represents the range of wave vectors which I have to use in order to construct the actual wave. And as a result, the wave extends in x space with an amount about delta x. And you see delta x, delta k multiplied together equals 2 pi. A shorter delta k value leads to a greater delta x value, and vice versa. This is yet another example of the uncertainty principle at work. The uncertainty principle is not only quite different from what we learn in classical physics, so it's something that you really take some effort to in order to sort of swallow, but it also is extremely powerful. Let's look at a couple more examples of how we can use the uncertainty principle to figure out things. The first example is something we learned before, the single slit diffraction of light. Single slit diffraction of light. We learned from physics 1c. If you have a single slit of width a, then you will get a diffraction central peak like this, right? And how do you find the edge of the central peak? So what is the value of theta 1? We learned that a sine theta 1 equals lambda. That's what we learned in classical physics, right? Now we can revisit this same problem from a different perspective. We think of the light as made of a whole bunch of photons. Okay, a whole bunch of photons. And these photons must pass through this opening in order to get there, right? Now we call this the x direction. We call this the x direction. Okay? In order to make sure these photons have made their way through, as they make way through, the photon must be located anywhere between here and there, and therefore it cannot be here, it cannot be there. There is a certain range where I can find that photon. So delta x, the uncertainty in its location in the x direction, is of the order of A, right? So if I narrow this slit, then I have greater and greater accuracy in the measurement of the whereabout of this photon in the x direction. But from the uncertainty principle point of view, if you can pinpoint where it is in the x direction, then you lose track of of its momentum in the x direction. The moment in the x direction has an uncertainty delta px, and delta px is about h bar over delta x according to the uncertainty principle, right? And that is about h bar over a. H bar over a. But what is delta px? Delta px is its momentum uncertainty in the x direction, and roughly it is of the order of the momentum in the x direction itself, order of magnitude. Okay, order of magnitude. So it actually moves, the photon will have to move along the x direction. It cannot only move along the y direction, because if it does that, then there is no delta px, because px equals 0, but delta x is not infinity, it's a, so therefore we would violate the Heisenberg principle. So delta px is roughly equal to this. Meanwhile, it also moves in the y direction. We call this the y direction. In fact, it primarily moves in the y direction, right? And therefore, can you find the direction of motion of that photon, given its x component and y component of momentum? Well, tangent theta equals py, or px over py. Remember, this is the x direction, and that's the y direction. Px over py. Okay? Now, px is roughly h bar over a. Py, the momentum in the y direction. Again, the primary momentum component is the y component, so it's almost the whole momentum of the photon, and it's related to its wavelength or the frequency in the following manner. E equals pc, so P equals energy, or hf, or hc over lambda. That's the energy of the particle, of the photon, divided by c. E over c equals p, remember? So c and c cancels, and what do you have? You have a over lambda. Oh, there's a h bar, so it's 2 pi. There's a 1 over 2 pi, but I don't really care that much about that 2 pi. Again, this is only an approximation. You don't have to have h bar, you can have h as well. And sine theta is roughly equal to tangent theta, because the angle is quite small. So you see, I get sine theta is roughly a over lambda, at least the order of magnitude. Okay, this is the precise result. This is our estimation. You see, they're really the same thing. All right, it's lambda over a, not a over lambda if you do the algebra. So we have a brand new perspective of the single slit diffraction. There is a reason why you will see an extended distribution instead of all the photons coming to converge at this point, because that would have violated the Heisenberg uncertainty principle of the energy of the momentum and uncertainty in position along the x direction. A photon coming through a very narrow slit would have a small value of delta x, the uncertainty in its position, and therefore it has more variation in the momentum in x direction, which means it has a chance to go further and further along the x-axis, so it will spread out even more. So smaller opening corresponds to larger value of theta 1, so that the profile of diffraction will extend further and further. So this, in fact, is an example of uncertainty relationship. Another example is atomic versus nuclear energy. Atomic energy, in this sense, means when you have chemical reaction with the electrons move in and out of an atom, how much energy difference is involved, how much energy transfer will happen in a typical chemical reaction. And nuclear energy is when the destructive nucleus changes, if it loses a nucleon and gains one or whatever, splits into two, whatever. What happens to the energy of the system? The atom is so much bigger than its atomic nucleus. The typical size of the atom is of the order of 10 to the negative 10 meters, but the nucleus only has a radius of the order of 10 to the negative 15 meters. So R over A is of the order of 10 to the negative 5. Now, suppose you have a particle trapped inside the atom. So it's, say, it's an electron, right, trapped inside an atom. So delta X, or delta R in general, just the uncertainty in its position, is of the order of A And as a result, the momentum of this particle cannot be just one single value, right? It has to have a range, right? Delta P is about h bar over A. And this is of the same order of magnitude of P itself. You cannot have a large P and a small delta. You cannot have a very large delta P and small P value. It doesn't make any sense. So it at least have to have delta P. So you see P is the order of h bar over A. And then suppose the particle does not move at relativistic speed. So the kinetic energy, K, of the particle is related to its momentum as P squared over 2m. So K equals P squared over 2m. And that's roughly delta P squared over 2m. And that's roughly h bar over A squared over 2m. Okay? And we can do a little estimation of what that is. This is, first of all, rewrite it as h bar and then 2m A squared and h bar squared. Before I start to work out numerical value, you know, h bar is a constant. Here's the mass of the electron. And this A is the size of motion of the electron. So this tells us that if you make this electron, confine this electron into smaller and smaller and smaller sizes, A decreases, the kinetic energy must shoot up. This is something very general, which comes from the uncertainty principle. You take a particle, right? You drop it into a box. The smaller that box is, the faster the particle must move inside, because otherwise you would violate the uncertainty principle. The smaller the box, the smaller is delta x, therefore the greater is delta p, and therefore it must have a lot of momentum. This qualitatively explains why there is more we can get from nuclear physics, nuclear energy than atomic energy, because the nucleus is such a smaller confinement, and therefore if you confine something to that small a size, you're going to get more energy out of it, because these particles must have a great amount of energy. But roughly, what kind of numerical value are we talking about here? To do so, let me introduce yet another important constant combination, and that is I'm going to multiply everything by c squared here and c squared. Then I have h bar c. H bar c. Now we know what hc is, right? Hc is 1240 nanometer eV. And you have to just divide it by 2 pi. 2 pi is about 6. So 1240 divided by 6. The answer is 197 nanometer eV. This is h bar c. We often use that as well. Remember, I asked you to memorize hc and memorize mec squared, and here comes something else that hopefully you can memorize as well. This will be more useful in nuclear physics than anything else. So h bar c, 197 nanometer eV. So don't take that number too seriously. It doesn't have to be 197, it could be 200 or something close to that, because we're only estimating. So this we're looking at about 200 nanometers eV. You square that, okay, and you divide it by 2. M a squared c squared. Let's write m c squared first. That is the rest mass or rest energy of the electron. Remember how much that is? That's 511 keV. So it's 511 times 10 to the 3 eV. Okay, and then times c squared. I'm sorry, a squared. A is 10 to the negative 10 meters, or it's about 1/10 of a nanometer. So it's 0.1 nanometer squared. You see how nice the units cancel out? Nanometer squared cancels out. Here you have eV to the power 2, here you have eV. So what's left is just eV. And how much is that? And the answer is a few eV. Okay, so this is the typical energy of an electron that lives inside an atom which has a confinement size about 0.1 nanometers or 10 to the negative 10 meters. This also explains why in a typical chemical reaction, when the electrons jump orbitals from one atom to the next, the typical energy transfer is of the order of eV. That's in chemical reaction. Now we all know that in nuclear energy, the energy involved per nuclear reaction is much greater. Why is that? Well, we can do the same estimation if we confine the particle to a much smaller size, 10 to the negative 15 meters, which is also known as 1 Fermi. 1 Fermi is defined as 10 to the negative 15 meters. We have the same formula. Of course, we really have to use relativity when it comes to nuclear physics because of high energy involved, but we're doing estimation, so that's okay. h bar c squared over 2 m c squared r squared. R replaces a, and this m is the mass of a nucleon, not the mass of an electron anymore. The mass of a nucleon, whether it's a proton or a neutron, they're almost equal to each other. They're about 2,000 times the mass of an electron. And so you have that expression. When it comes to nuclear physics, h bar c, it's easier to express it in terms of Fermi and MeV instead of nanometer and eV. You go from nanometer to Fermi, you have you drop by power of 10 to the 6, but you go from eV to MeV, increase by power of 10 to the 6. So they're equal to each other numerically, 197, either nanometer eV or Fermi MeV, the same. Okay, so you have Fermi MeV squared divided by 2, mc squared, m is 2,000 times the mass, the rest energy of an electron is 0.511 MeV or 511 keV, same thing, times 1 Fermi squared, that's the rough size of the nucleus. And if you did that, you'll find the answer is very simple. It's about 1 MeV. This is far greater than the energy of an electron trapped by an atom. So this simple estimation tells us there is far more energy to be harnessed in the atomic nucleus. And this makes total sense from the point of view of the uncertainty relationship, because we're looking at a very tight confinement. The tighter the confinement, the greater the energy this thing must have, because it's greater variation of momentum. And this result, even though we have very simple calculation, this result agrees very well with nuclear physics. In a typical nuclear reaction, at a nucleus change into something else, the typical energy change is of the order of 1 mega electron volt. This is why nuclear energy is really far more efficient than chemical energy in a chemical reaction. So hopefully in this chapter we have some idea of the basic notion of quantum mechanics, and again at the center of that notion is the wave-particle duality, which de Broglie proposed from observation of the particle nature of waves and wave nature of particles. And then we started to use a wave to describe a particle, and the inevitable result is the Heisenberg uncertainty principle. In the next chapter, we're going to get deeper into quantum mechanics. We're going to use an equation. We're going to establish an equation, which is called the Schrödinger's equation, which will allow us to find the wave function. And it turns out if you have the wave function, you have everything. You will know everything that you can know about the system. It's just like Newton's second law, which gives us everything about how a classical particle moves. We'll see that in the next chapter.